Hey friends, it's video 24. This is one where I'm not going to use our studio for the moment. Oops, getting texts. How very professional. This is the video where yes, okay, Emily. This is the video wherein I talk about the assumptions underlying OLS, ordinary least squares regression. Um, OLS is the basis of our toolkit in political science, but it has some pretty strict assumptions that mean that when you use OLS and you're violating the assumptions, OLS is potentially a misleading tool to use. So in the last couple of weeks of class, we're going to talk about some different, we're going to talk about some kind of alternatives to OLS. Leaving that aside, though, I think I'm going to go through these assumptions in sort of a theoretical way, and then in class we will talk about, I'll show some pictures. But for now, I just want to talk through this sheet, which is going to be also posted on Blackboard. So I strongly advise you to, print it out and carry it close to your heart and study it all the time, or at least keep thinking about it, because there will be a quiz on this stuff. It's really important, etc. All right. So there are, roughly speaking, people have different, again, with different statisticians having kind of different ideas about this. There are about 7 assumptions. The first one is no, thank you. The first one is accurate measurement, and that is to say, we want measurement error to be error, not bias. So measurement error, accurate measurement, this is the first row. In English, that means your measurement error is random rather than systematic, and importantly, you want it to be small relative to the variability of your variables. So if you have, very large measurement error on variables that don't actually move around that much, that's going to swamp the effect of a given independent variable. Just saying. What will go wrong? Everything. And this is key to me. I think this is so important that it's not obvious that there's a good way to check. Like there's not a test you can do or a graph you can look at. You have to be thinking creatively about ways that missingness or error could be systematic. There are some solutions. We'll talk about what sensitivity testing and imputation mean. Better measurement is kind of obvious. Like, if I'm using a kind of weak measure of my concept, maybe I should consider a different measurement. We'll talk more about what that means. The second assumption is accurate specification. Now, when we say specification, we mean basically what independent variables are we including in the model. So in multiple linear regression, I know you haven't seen it yet exactly, but in multiple linear regression, the kind of joy of that tool is that it allows us to include multiple different independent variables, that is, possible causal variables that are affecting our outcome or our dependent variable, and we actually get to compare them against one another. Woohoo! Accurate specification assumption says that all the relevant variables are included and no irrelevant variables are included. The first part of that is much more important than the second part of that, because omitted variables bias the coefficients and standard errors. So for example, if we think about a bivariate regression in which the percent of people living in rural areas in a given county is somehow causing or associated with the percentage of people voting for Trump in that rural county, that's omitting a lot. And we can tell it's omitting a lot because if we were to look at that association, there would show a sort of linear trend, but the linear trend would be quite variable, and there would be some rural counties that that voted against Trump, obviously, and there would be some extremely urban counties that voted for Trump and all of that. And so what you need to do then is to be thinking about alternative explanations. So is it really ruralness, or is it something about whiteness, or is it something about education levels, or right? We can go on and on. And the way to solve that problem is just to make sure that you have all of the theoretically relevant independent variables there. So it's better to start with a kind of bigger model and remove things than it is to sort of be like, yeah, being rural explains it all, because that's obviously not true. The third assumption is linearity, and that is to say the true relationship between X, or your independent variables, and Y is linear. So because, kind of like correlation, ordinary least squares really only measures a linear relationship if you've got something exponential, or if you've got a curvilinear relationship of some sort, you're going to get the wrong coefficient. For example, you might do something like the example of no correlation except there's a clear U-shaped curve, right? The relationship is there, but it can't be detected if it's not linear. So the way to check for that is to really just look at a scatter plot and say, oh, whoops. And there are some ways of dealing with that. You can transform X or Y or both. Common transformations include squaring or taking the log, and we'll look at that more in class. This is a fun word. Assumption 4 is homoscedasticity. Hey. So the violation of homoscedasticity. So homoscedasticity, yay. Heteroscedasticity, boo. And basically, the spread, so that's the spread of the residuals, the distance from the real Y to the estimated line. That's the kind of red distance in the previous video. We want the spread of the residuals to be constant for all values of the independent variable. That sounds really abstract, but what it basically means is that you shouldn't have more variability or more measurement error or more whatever as the values of your independent variable get bigger. So common examples are looking at the relationship between GDP and Civil War violence. So GDP is our X. Basically, for low values of, right, for almost all rich countries, there's no Civil War violence, so very little variation, around 0. But for poor countries, there's tons of variation, because there are poor countries with no civil wars, poor countries with really violent civil wars, etc. And the shape, we'll talk about this more in class, the shape of heteroscedasticity is often something that I refer to as the cone of shame. And that is, you look at the scatter plot and it's narrower over here than it is over here. Again, we'll talk about it more in class. So you can look at a scatter plot, and you can also do a Breusch-Pagan test. Breusch-Pagan test, again, something we'll look at in class, but it's a one-liner. You fit your model, you do a BP test, and then you can see. The problem is that if you have homoscedasticity, you can't use OLS. You can kind of fudge it if there's not terrible homoscedasticity, but there are other models, and if people are interested, we can talk about that. But it's not a situation that is fixable with OLS. No autocorrelation. This means that there's no correlation between observations on the dependent variable. The most common situation where we find that is basically what's called a time series. So if your observations are repeated measures, let's say Donald Trump's approval day to day, then usually the best predictor of today's Donald Trump approval rate is actually yesterday's Donald Trump approval rate. And that is going to mess you up. So if you have reason to believe that there's any kind of correlation or relationship between sequential observations of the dependent variable, you want to do something about that. You can, first of all, just kind of consider whether one observation predicts the next. And you can also do a test called a Durbin-Watson test. Much like a Broich-Pagan test, it is, it's a one-liner. I'll show you how to do it in class, not hard. And the way to fix that is actually kind of elegant. You just include a so-called lagged dependent variable as an independent variable in a multiple regression. So a lagged dependent variable is basically, if the best predictor of Donald Trump's approval today is Donald Trump's approval rating yesterday, then the right thing to do is control for that by including it as another independent variable. And I'll talk about how to do that again in class. All right. It's also an assumption that the expected value of the error, so again, error is random, not systematic, and it should be centered on zero and roughly normally distributed. Centered on zero is probably more important, and normally distributed is not exactly optional, but people don't really bother you if that's not true. Yeah, anyway. And the way, so you'll get the wrong intercept, but not the wrong coefficient. The fun thing is that once you fit the model, you can just look at a histogram of its residuals, and I'll show you how to do that in class. There are ways to fix that, again, by transforming X or Y or both. Most of the time, people kind of let it lie. Sometimes it indicates that something else is wrong. So what you want to be able to do is just go through the checks on this page. You want to understand conceptually what each of the assumptions means. Then you want to think about, okay, have I checked all of this stuff for each model? The final assumption is non-collinearity, and that means this is only for multiple regression, so only for a situation where you have more than one independent variable. And it basically means the independent variables are not too strongly correlated with one another. What happens when you have highly correlated independent variables in the same model is that it's actually really difficult to understand which of these highly correlated variables is so-called doing the work. If you have, if you're trying to measure education and you include both the high school dropout rate and the percentage of people with a BA degree or higher, those are going to be extremely highly correlated, but you're not going to know, right? Is it something about the college experience or lack thereof that's doing the work, or is it something underlying kind of inability to get through high school? So you want to remove, what you do is just remove the less theoretically important of your highly correlated independent variables. So I want to close with a small pep talk. It's really, these are important assumptions, and I know that this page is a ton of information. But after we look at some examples, I think that it'll kind of settle into place in y'all's heads. So start thinking about it, but don't be freaked out if it doesn't seem intuitive yet. Also, you might want to practice pronouncing homoskedasticity or heteroskedasticity, because, that's a hard thing to say. All right, see you in class.